Welcome to our chapter on waves. Our first topic is going to be waves. We're going to be looking at the concept and the anatomy of a wave. I would like to start out by pointing out the difference between ocean circulation and waves. So in the last chapter we talked about the gyre circulation, and in ocean circulation we are moving actually a mass or an object around the ocean basin. Look at the image on your left and pick one of these circular gyres. So for example, the one in the North Pacific. Now imagine we would take this duck and put it in the ocean off the coast of Japan. The duck would move along the major ocean currents around the gyre. Eventually the duck would end up again off the coast of Japan. Waves, on the other hand, even though they seem to be transporting mass, they do not. They're just moving energy. And I'm going to talk about this more. So in this slide, we're looking at the difference between circulation and waves. In ocean circulation, that we covered in the last chapter, we are actually transporting mass. So Ekman transport, Ekman spiral, geostrophic flow, all these concepts count. And because we're moving and we're moving mass, circulation is affected by Coriolis. Just think about gyres. So if we look at the northern hemisphere, this gyre circulation is clockwise, and the southern hemisphere counterclockwise because of the Coriolis effect. Waves, on the other hand, do not transport mass. They're just transferring energy. Therefore, they are not affected by Coriolis. And as an example, think about stadium waves, when people lift their arms but the bodies are not moving, the people are staying in their seats. That's an example of energy transfer in a wave. So this image demonstrates that waves travel ahead, but the water itself does not. So in the sequence you can see here, a top moves from the left to the right as the gull, and also in the water the gull is resting, revolves in an imaginary circle, moving slightly to the left, going up, and to the approaching wave, then to the crest, and finally moving to the right, down back of the wave. So these kind of waves are also called orbital waves because the gull and also the water molecules, they move in orbits. And they're also called progressive waves because the wave is moving, but your objects are not. So here's the concept again. Waves transmit energy, not water mass, across the ocean's surface. Because waves have no mass, they are not affected by the Coriolis force. Ocean waves are also called orbital waves, in which the water molecules move in closed circles or orbits as the wave passes. In this slide, we're going to be learning some terminology for waves. So this diagram shows you the anatomy of a progressive wave. This diagram is in your book, and I recommend that you spend some time looking at it and studying it so that you can understand the different terms. So first find the dashed horizontal line. This is the still water level. So if there was no wind and the water would be totally flat, that's where the water level would be. Hence, still water level. The yellow arrow on the top indicates the direction the wave is moving. So the wave crests are the highest points on the wave, and the troughs are the lowest points. So we can measure the wavelength from crest to crest. So here indicated by the A and B, or we could also measure it from trough to trough. The wave height is the height difference between the crest and the trough. Under the B, you can see a circle. This is supposed to show you the orbital path of individual water molecule at water surface. And then there are two more terms. One is the frequency. That's the number of wave crests passing point A or point B each second. And the period is the time required for the wave crest at point A to reach the wave crest at point B. How deep can the effect of a wind waves be felt? So again, this is the similar diagram like in the last image, direction of the wave motion into the same direction. And now you can see the wavelength indicated from crest to crest, and you see all these orbital waves being drawn in. The effect, how deep the wave can be felt, is half the wavelength. Let's think about it again. So let's say that the wavelength is 2 meters. Half of 2 meters, 1 meter. So if you dive deeper than 1 meter, you're not feeling the wave motion near the surface of the ocean. Under the required readings, I posted a website where you can just see yourself how changing wind strength is affecting the depth to which the wave is being felt. Waves are classified by their physical characteristics. So wave energy in the ocean is a function of the wave period. And as the graph shows, most wave energy is typically concentrated in wind waves. However, large tsunami, which are rare events in the ocean, can transmit more energy than all the wind energies for a brief time. So the waves are formed by a disturbing force. And in this case, it's the wind that is doing the disturbing, or in the case of the tsunami, it is the seismic disruption. And then we have a restoring force that flattens out the water surface. And the wavelength, this is what is the most useful measure of a wave size. So we have capillary waves. These are these tiny ripples in the ocean, or it can also be in a sink or in a bathtub. And it is the surface tension that wants to flatten that wave out again. And then we have wind waves, and we have seiches and tides, and here it is gravity that wants to flatten out the wave. So the behavior of a wave is influenced by the depth of the water through which it is moving. So again, find that dashed line. This is the depth where the wavelength is 1/2. When the wave travels in water that it's deeper than 1/2 its wavelength, we call them deep water wave. And you can see it's written out in the bottom. Deep water waves, depths greater than half the wavelength. So the c is the celerity, the velocity, the wavelength, and the wave height is constant over a long distance. Now as the wave approaches the shoreline, it's going to start feeling the bottom because the wavelength, the depth of the ocean is going to be not as deep as half the wavelength. And it's starting to feel the friction. And this wave turns into a shallow water wave. A shallow water wave is defined when the water depth is less than the wavelength divided by 20, and the wave breaks. And anything between deep water waves and shallow water waves are called transitional waves. Let's do a little bit of math. Let's calculate this velocity of a wave. So instead of using the v for the velocity, we're using the term c for celerity because waves don't have a mass. So for deep water mass, we can calculate the celerity by taking L, the wavelength, dividing it by time. And you can see that the c and the L, they are proportional. So the longer the wavelength is, the faster the wave is going to be traveling. And these are deep water waves, where the depth is greater than half the wavelength. So this wave does not feel the bottom of the ocean, so there is no friction. The celerity is calculated differently for shallow water waves. So this is for waves where the depth is less than half a wavelength. So the celerity equals the square root out of the acceleration due to gravity times d. So in the formula that you see here, the 9.8 meters squared divided by seconds squared, which is the acceleration due to gravity, has been pulled out. So the celerity equals 3.1 and the square root out of the depth. You can see that the wavelength no longer is in the equation. As soon as a wave is a shallow water wave, it is automatically determined, the speed is determined by the depth of the ocean, by d. So let's do one quick concept check questions before we are moving on. So imagine you have a wave that has a wavelength of 200 meters. And this wave is now in water that's 50 meters deep. Is this wave a deep water wave, a transitional wave, or a shallow water wave? It is a transitional wave. Yeah, let me show you the calculation in the next slide. So a wave with a wavelength of 200 meters is what in 50 meters? So for it to be a deep water wave, we have to take the wavelength and divide it by 2. 200 meters divided by 2 is 100 meters. So for this wave to be a deep water wave, the water has to be deeper than 100 meters. And a shallow water wave, the wavelength, the water has to be shallower than the wavelength divided by 20. So 200 meters divided by 20 is 10 meters. So if the water is less than 10 meters deep, this wave would be a shallow water wave. But it's at 50 meters, so it's between a deep water wave and a shallow water wave, and therefore it is a transitional wave. So this concludes our first topic.